Me today is Sarah Sleesman and Rebecca Gorelli from ADE. Sarah or Rebecca, would you like to say anything?
I don't really have anything to say. I would just like to thank you for being here, Sarah, and thank you for Arizona educators for coming to be in this space with us today. My name is Sarah Sleesman. I'm the Science and STEM Director, and we have Rebecca, who is our Science and STEM Specialist, here to support Sarah and you through our journey together today.
You. Rebecca?
Yes, hello. Of course, I have something to say. I am the one who's been emailing you. Hello, everyone. The way this works for PD clock hours is you just have to engage in the experience for the entire time, and then please wait about 24 to 48 hours. I have to take the Zoom attendance and then put it into a different system. So it takes me a little bit of time to do that. And once I do put it into the system, it'll automatically send you a survey to complete, a very short survey. Let us know how we did. And then once you complete the survey, you will print your certificate from your ADE Connect account. And I'll send a follow-up email once I'm done with attendance. That way you know you're good to go and you can print it on your own. And I'm happy you're here. Yay, excited to do this. Thanks, Sarah.
Thank you. Thank you, Rebecca, and thank you, Sarah. I am delighted to be with you today for some of you I know have been with me before in regards to learning about the science and engineering practices, the cross-cutting concepts, and the core ideas. And today we're going to put them all together and see what it's like and when we put them all together. So to start off with, I'm going to put a little poll in just to see who is in the room with us today. So you should see on your screen a poll. If you wouldn't mind completing that, just kind of give me an idea of who's here.
Sarah, this is Marie. I don't know if you can hear me or not, but I'm not seeing a poll. I'm going to exit out and rejoin if that's okay.
That will be fine.
Okay, thank you.
All right, looks like most people have completed the poll. I'm going to share the results with you. You should be seeing the results. Looks like we have people from all grade bands, which is wonderful. Majority are 6-8, and I think that will be wonderful. This will be the lesson that we're going to kind of experience today is actually could be done at the 6-8 or high school level. But do not worry, pre-K2 teachers and 3-5 teachers, because what you do is foundational for the knowledge level that's needed in this lesson. And we have a variety of different people who are here, so thank you so much. Lots of classroom teachers, and I just want to thank you for your dedication and for being here after hours and continuing to learn. Thank you, thank you, thank you. Quite a few of you have participated in some of the previous professional learning. Those that have not participated in any of this, I'll give you a quick summary of the other three professional webinars on cross-cutting concepts, science and engineering practices, and core ideas. But I would suggest that in the future, go ahead and sign up for those as well. So let me stop sharing results. So for our time together, the microphones are disabled, but I know you will be talking and having discourse. So there'll be times when you'll be able to take off that microphone and use it. But go ahead and use the chat room as well. Rebecca and Sarah are here as well as I am, kind of keeping an eye on the chat. So we will put things in the chat as we need them. So please utilize that as we go through. And if you haven't already, I did put this in the welcome. If you have the materials, some 70% rubbing alcohol, a couple pieces of ice, and a clear plastic or glass cup so that you can just kind of see some. If you have these materials, if you can put a Y in front of your name, that just will help me as we put you in breakout rooms to ensure that everybody has somebody in that room with the materials. So thank you very, very much. During our time together, this hour and a half, my goal is to help us shift the way we think about teaching science. And I have really three objectives as we go through our time together. One is I want you to experience a three-dimensional lesson and see and reflect on that as a teacher, thinking about what were those strategies used and thinking about how those strategies were used to help students, to help our scholars understand the how and the why of our core ideas. And so that is what will be what our goals are for the day. Let you know you will get a copy of this presentation, so do not feel like you have to write down every single word, and you'll get a resource page. So those things will be coming with you to you tomorrow from Rebecca. She'll be sending those out with other materials. Our norms, just like we have norms in our classrooms, I'd like for us to use our vowels. I want you to ask questions. I want you to integrate this information in your classroom and also utilize what you learn, but be willing to share it with others and help others learn as well. So just as kind of making sure we all have the same foundation, our Arizona science standards that were adopted in 2018 have these three dimensions that are intertwined together in our standards. And the first one is what we call science and engineering practices. These are the tools. This is the doing of science. This is what scientists do and engineers do. They ask questions. They have arguments with others and discourse, and they carry out investigations and they analyze data. And we want our students to do the same. So that's one of our dimensions of our standards. The second dimension of our standards is the cross-cutting concepts. I'm kind of jumping to the green on the screen. The cross-cutting concepts are really like, and those of you who know me know they're my passion, they're my love. They're the tools that our students, our scholars can use that help them organize and connect the dots. They build upon the neurons, and there's 7 of them, like patterns and cause and effect, stability and change, energy and matter. And so it's a conceptual framework that allows the students to connect the dots and make sense of new information. And the new information that they're getting from is our core ideas. And this is what we always think of when we think of science and our science standards: the earth and space content, the life science content, and the physical science content. And those are our core ideas. And our standards are built that they intertwine those 3 dimensions. And that's what we call 3-dimensional standards. But with our new standards, since they have this intertwining effect, it's going to require us as educators to kind of shift the way we teach. And so there's 3 big shifts that we have to think of. The first one is that we want our students to be able to explain phenomena and design solutions to problems. Not for us to explain it. It's not the educator who needs to explain it. It's our students who need to be able to voice it and explain the phenomena. And secondly, to be able to explain it, they need to be doing the science. This is where that dimension of science and engineering practices comes right on in. They're going to be doing the science to be able then to explain the phenomena of what they're figuring out. And the third shift is that this is done in a very coherent learning progression over time. It's not all going to be done in just one grade. And it's vital that K through 12, and I would really say pre-K through 12, needs to be on board and be teaching science consistently throughout that time. And that's only fair to our students and for us as educators. So these are the 3 shifts, and this is taken from NSTA, from their distance learning strategies. If you were with me last week or have been attended another core idea, one of the 3 dimensions of science, you've seen this slide before. And just kind of, this is how that content, that core idea progresses over time. Our young scholars, our K2 scholars, need the opportunity to be able to do science and look at things that sink and float. That basic understanding builds upon for the next level of upper elementary that is focused on these particles in materials and what those particles are. And those particles, when we look at these solutions and mixtures, they're going to be able to understand, oh, they're concentrated, and what does that look like at the particle level, which will then build upon the understanding to be able to figure out the third picture for where we see those bottles of liquids. And students will be able to understand, well, because they're at different levels, there must be something to do with the particles and the spacing between the particles, which we may call the word density, right? How much stuff is in those liquids, which then helps the students to be able to understand convection currents and weather patterns and how we gain, why we have weather and how we understand convection currents. Now, so that helps us then build upon high school knowledge as well. And looking at that last bottle, that last picture of, ooh, these beads float in the middle. But those of you who were with me in the past, you know I can shake that bottle up. The beads separate. The white beads float on top. The blue beads float on the bottom for quite a few minutes. And then they start to shift around. Again, understanding those basic principles from the pre-K2 level helps them build that foundation to be able to figure out the phenomena that's happening at the high school level. So it's that progression over time. So today, I'm going to ask you to wear 3 hats. One, I want you to put on a student hat as we dig into a lesson and think about how a student would respond to the learning. During that time, I know you'll have your teacher hat on. We always do. It's hard for us to take that teacher hat off. And so I want you to kind of think like a student, but I want you to note how the teacher guides, okay? How is the teacher guiding this lesson throughout? And then we'll come back and we're going to take off that student hat and we're just going to keep our teacher hat on and reflect on the experience and what were those teacher moves that allowed the student to be engaged in figuring out the phenomena. So you'll see these hats throughout our time together, but I just wanted to kind of give you an overview that you will be stepping into the student mode for a while. At this point, what questions do you have? I'm not seeing any and I'm not hearing any, so I'm going to move on. Okay. So we're going to set the stage. This is probably a lesson that can be done at high school, but definitely can be done at middle school level. And we have been, and I'm not, there might be things we've taught before, or might things that come after. But in general, you have been studying matter. and or materia, but you have been studying matter in our class. And we've been mainly focused on water as the main universal substance. And through matter and studying this, you understand the phase changes and what happens at the particle level between a solid, liquid, and gas. So just kind of give you that information so you can feel like, okay, this is what I know as I go into this lesson. I know gases, I know liquids, I know solids, I know how the particles are different between those phases of matter and can describe them. So that's where we're at. A thumbs up on that? Okay. Well, scientists and engineers, are you ready to go into class? All right. I see Raina's giving me a thumbs up and Susan is too. Welcome, scientists and engineers, into science. I am so delighted that you are here today. We have been studying matter, and today we are going to study a little different types of matter and compare some things. But what I need you to do, if you can get your science notebook out for a moment and create a table, a 3-column table, an I see, an I think, and an I wonder table. Can you do that for me? Okay. Hopefully you have that. In a moment, you're going to watch a video, and in your alone zone, I would like for you to record your observations. Remember, record your observations, what you see, okay? And you'll do that, what do you see? What do you think might be happening? And in the I wonder, would you record any questions that you might have, okay? So the I wondering is, I wonder if we did this, what would happen? There are types of questions that you may have. So record your observations in your notebook. The I see, I think, I wonder. This is a very short video, so you are such experts and we've been studying water for so long. I think you probably don't need to watch it twice. But when we come back and you say, hey, can we watch it one more time? I want to record some more observations. We can do that. But I think you'll be fine watching it once. Okay, I think everybody has their table ready to go. So let's go ahead and watch this. And let's Okay. I'll give you a couple minutes to write down your observations. Does anybody need to watch it again? Everybody's okay? All right. Okay, scientists and engineers, I know you're finishing up your writing down some of your observations about what you saw. But let me tell you what you're going to do next. You're going to get in a breakout room and you're going to have two moves. And when you first get into the breakout room, you're going to be in a breakout room a couple different more times. So you may want to choose some roles to take when you're in the breakout room. Somebody that can be a facilitator to ensure that everybody's on track. As somebody who can be the timekeeper for this breakout room, you'll have 8 minutes and somebody to come back and be the reporter to share out with the whole group. So you might want to determine those roles. And again, as I said, you're going to have, you're going to have two main moves when you get into the breakout room. Now, first of all, when you get into the breakout room, your first move is that you are going to talk. Now, I know that means you have to unmute yourself, and scientists and engineers in this virtual setting sometimes don't like to unmute themselves, but you're going to have to unmute yourself and share your observations, okay? And then I want you to talk about them and then choose two, just two, and you're going to record your personal two. Everybody in the breakout room is going to choose two and individually record them on a sticky note, on a blue sticky note on the Jamboard. Okay, so if there's 4 people in the breakout room, there should be 8 blue sticky notes on the Jamboard when I look at them. All right, so individually put those down. The second move, once it quiets down, and you can kind of see that you and your fellow scientists and engineers have put about your 8 Post-it notes, your sticky notes on the Jamboard, I'm going to ask you to look at them and individually circle one that you did not notice. It was an observation that you did not record. And then put a check mark next to those that are the same thing that you wrote down. And you might have multiple check marks. Then I want you to discuss again. Again, this means you have to unmute yourself and talk to your fellow scientists and engineers in the room and discuss what pattern or patterns did you notice about the investigation, okay? And put those in green. Did you notice any patterns between those 2 cups? And if so, what was the patterns in that investigation? So let me share with you, in case you're new to the Jamboard, on how this works. There's one Jamboard. We have enough rooms for one Jamboard. When you get on the Jamboard, when you click into your breakout room, you need to pay attention to what breakout room you're in. So you're going to get a little message from me. It says you're going to go to breakout room 3. Just remember you're in breakout room 3, okay? And then when you get into your Jamboard up here at the top, you can change your frame. It's from frame 1 would be breakout room 1, frame 3 would be breakout room 3, and so forth. The directions are on the Jamboard, so you don't have to trying to remember all those moves I just told you about. To add a sticky note, the sticky note's right here. You click on that on the side of the Jamboard, it'll come up. You can change your color. Remember, I want some in blue and some in green. So no yellow ones, okay? All right. And then you can use the pen to mark it as you draw your circle and your check marks. So before I let you go and put you into breakout rooms, let's first double check. You should be able to open up that Jamboard, and the link is in the chat. So let's check and make sure everybody can do that. And secondly, what questions do you have before I move you into breakout rooms? I'm not hearing any questions. Rebecca, would you summarize what I'd like people to do in the breakout room?
Absolutely. So let me just repeat to make sure we understand is we're going to go into the breakout rooms, but one thing we need to remember is what room are we going to? Because that's going to help us. So as soon as we see the button, pay attention to the number. That way, when we get into the Jamboard, we know which frame to go to. And just make sure we can open the Jamboard. And then we will do the moves that are listed in the Jamboard with our group.
And you have how many minutes? Ah, you have 8 minutes. 4 minutes.
Minutes.
I see people pulling up their fingers. Okay. 4 minutes for about 4 minutes for each move. So timekeeper, if you can kind of keep track of that. I will give you a countdown of 30 seconds when there's 30 seconds left. Scientists and engineers, go ahead. I'm gonna start the breakout rooms now. Maria, did I not assign you? Let me see. Christina, I'm going to put you in room 4. Maria, do you see you should have been to room, should have gotten an invitation to room 3. Do you see that invitation? Welcome back, scientists and engineers. Your rooms are closing. Okay. Let's take a look at the Jamboard. and some of the observations you made. And if the reporter wouldn't mind kind of giving us a one sentence summary of like the main things that you may have discussed or an aha that your group discussed while you were sharing your observations. And we'll start, I like to always we're going to start at the very end with room 5, breakout room 5. So if the reporter from breakout room 5 would like to share.
Well, we didn't get to that point. But we just go into the discussion. So our discussion was just looking at, we saw the same things more or less, but the aha for us was somebody actually broke it down. They saw, I saw in each one 2 ice cubes and how many milliliters of liquid in each beaker. And another person shared, she felt that the containers were different sizes. It's not something I noticed, but she seemed to have noticed that. She's not sure, but she seems to have seen that the beakers were different sizes. And because of the different sizes, maybe the alcohol looked like it had more alcohol than water, just by the perception.
Great, thank you. And the fact that this pattern of, ice sinks in alcohol and it floats in water, that might have been a pattern that, based upon our experience before, right? We have been studying water as this universal liquid, right? And so we've done a lot with water in the past couple weeks. So you're seeing that same pattern coming through. Let's go ahead and we'll look at room 4, breakout room 4. The reporter, would you like to share what your main thoughts? How are they similar or different from the other room?
I was in group 4. We did not get to who was going to be the reporter, but Raul, Donna, or Christina, do any of you want to jump in?
I can jump in on that. This is Donna.
Great, thanks, Donna.
I also noticed that the ice sank in the alcohol. The ice also floated in the water. We talked about the fact that we had some wondering questions on whether it had to do with ice pockets in the ice because the ice was the same shape. We had more wonders than anything, I think, was that we wondered what would be the makeup of the alcohol to cause the ice to sink versus float like in the water.
Ooh, great question, wonderings. Okay, so hold on to that because that's going to help us as we continue this investigation. Thank you, Donna. And I liked how you had some that you noticed as your pattern that there was pretty much the same variables. You were dealing with a clear liquid, have some ice cubes, but some different results. Wondering why. Okay, let's take a look at breakout room 3.
Hi there. Okay, for breakout room 3, what we had put on our sticky notes was that we observed that in the beaker where there was, when the ice was added to the water, the ice went to the top, and when the ice was added to the alcohol, it went to the bottom. And so that was pretty much consistent with all of us is what we saw, and we talked about that for a while. So we didn't actually get to the pattern part of it, but that was our observation.
But with the check marks on all of those things that you all saw the same things, that kind of helps you think about these are patterns that we all noticed, right?
Right.
So helping with those check marks, even though you didn't get it on this green sticky note, we can tell that that's what you were thinking. So great, thank you for putting the check marks because that helps us as well. Oh, great, thank you. Let's go to breakout room 2.
So pretty much what a lot of the other groups were saying, we noticed, we identified the types of material being used, and that in the beaker with alcohol, the ice sank, whereas the one with water floated. And that was the pattern that we identified.
Great. Thank you very much. And I love how you use some of these great vocabulary words of liquids, putting that onto your Jamboard. I can see that. So thank you very much, scientists and engineers, for using our scientific vocabulary as we move along. And then let's not forget breakout room 1. Go ahead.
Yeah, I think it's pretty similar to what all the other ones have said, but our main notice was that the ice sank in the alcohol and floated in the water. But what someone else noticed was that the alcohol they used was 90%. And that really stuck out because we were asked to bring 70%. So we didn't know if that could make a difference.
Yeah, wondering. And I also see that people were circling that there was bubbles. I wonder, scientists and engineers, you notice, I'm really great on that. Great observation that you noticed it was 90%. Did you see a title on the tube that said it was water? You wouldn't think that Mrs. Torres would trick you, would you? Okay, well, let's move on. We'll just have to think about that one, right? And so what are some of the wonderings? I know I didn't ask you about all the wonderings you had, but we had one wondering from Donna. Or were there other wonderings that you had that can help us kind of think about why would ice cubes do something in one container and not the other? What were some? Go ahead and put your wonderings in the chat. Let's see what kind of wonderings we had. I see them coming in, quite a few different ones. Does it make a difference about this type of alcohol? Oh, what's the different varying effects? What's the temperature? Does the temperature make a difference? Ooh, I like that thinking of could we change something to vinegar? Great questions. But why did the ice sink, but the ice and the other liquid float? Yeah. We're gonna kind of think about that question. And we have the word melt. Again, one of our words that we've been using as we talk about phase changes throughout our time. Ooh, Rhonda, did you see, everybody see Rhonda's question? I wonder why ice wouldn't dissolve in alcohol. Does it dissolve? Do we know that? We have lots of things we could investigate. And if we had lots of time when we get done, we might want to try some of these other things out. But what I'd like for us to think about today is really, let's kind of focus in on, as we think about that idea of why would that ice float in one and sink in the other? What is that composition of that one liquid that would make it sink or make it float? What's happening there? And would it always stay like that? So we're going to kind of investigate that some more, if you don't mind, scientists and engineers, we go through that. So what I'd like for us to do, because you all have your materials, or quite a few of you have your materials, let me share with you, we're going to investigate this ice and alcohol phenomenon and why in the world does it sink in the alcohol? What's causing that to happen? And what does that system look like? So in a few minutes, I'm going to put you back in your breakout room, and you're going to continue to use that I see, I think, I wonder table. But I want you to draw a line through it right now. Put where you have your top observations, draw a line, because this is going to be a new set of observations you're going to make. But you're going to still use that same table. Okay, I saw Raul draw this line. Okay, so when you get into your breakout room, you're going to make some more observations of a system. And I want you to watch the behaviors of a system, okay? And the system that you're going to observe is you're going to, when you get into your room, you're not going to do it right now. When you get into your room, you're going to take some rubbing alcohol, okay? And if you have a cup, fill it about a cupful, like, 100 milliliters, 200 milliliters. If I have this big of a cup, I'd probably fill about halfway, all right? You want more alcohol than ice, okay? We want more alcohol than ice. Then after you have your alcohol in here, put 1 or 2 ice cubes in. Now take a look at my ice cubes. My ice cubes are kind of big, they're chunky, they're coming out of an ice maker. If you have small little chips of ice, like I want you to use like 5 pieces of chips of ice. But if you have big ice cube chunks like I do, then I only want you to use 1 or 2, okay? So when you get into your room, all of you that have the materials, go ahead, pour your rubbing alcohol in. For this glass, I'd fill it about halfway. Put a couple ice cubes in, and then record your observations for 5 minutes. Now, those of you who don't have the materials, you have a really important role. And that role is that you have to ask lots and lots of questions. Okay? You need to have them say, you need to say, hey, I can't see that. Put it up to the camera. Tell me what it feels. Waft. Use your senses, but do not taste. Okay? All senses, but no taste. Okay? Scientists and engineers, we know that, right? So use your senses, not taste. Okay? But if you don't have the materials, that's your role, because you have to record observations too. And the only way you can record observations is if you ask questions about what's happening, okay? So you'll have 5 minutes to do this. And then I'm going to call you back into the breakout room. If you have this, don't throw it away when I call you back in. Keep it going. We're going to keep watching this for like 30 minutes. But in 5 minutes, I'm going to call you back in, all right? So Susan, you're shaking your head. Yeah, I got it. Do you mind? Can you do a quick summary of what I want you to do when you get in your breakout room?
When we get in our breakout rooms, we're going to put some alcohol in our cup and add a couple ice cubes, depending on the size of the ice cube. And then we are going to observe, making sure that if we have people in our group who don't have the materials, that they can see the observation on camera as well and record.
And when you're recording your wonderings, think about questions about the behavior of the system. How is the system behaving? Okay. Now, I don't want you to come back that the system is behaving good or the system is behaving bad and it needs to go see the principal. That's not appropriate. Okay. So scientists and engineers, think like a scientist, write like a scientist, talk like a scientist. I know you can do that. Okay, I'm going to move you into your breakout room. You'll have 5 minutes. Christy, were you in a room before? Maria, you should be going to room 3. Do you see that? You should see your invite at the bottom of the screen. Christy, piano, or can you hear me? Okay, you should still be making observations. Now, this is what you're going to do next, scientists and engineers. I'm going to put into the chat a document. So in the next 8 minutes, you're going to go back into your breakout rooms, and let me share with you what you're going to do. You're going to continue to observing, ask questions about what you are seeing with that alcohol and ice. But on this model's explanations sheet, which I put in the chat, you can open that up. You should see something like this. Good, everybody's coming into it. You're going to do what with the very first part of this in your alone zone. It says 10 minutes, but I'm only going to give you 8 minutes because you're really advanced and I know you can handle this. But you're going to create a model to explain the alcohol and ice phenomenon. Okay, so you're going to create a model. And then with that model, you're going to create an explanation through words of your image. And you may want to use some questions I'm giving you here in the document to help you with that explanation. So we're only doing this very first part, the alone zone part. So let me share with you what that means, what that looks like. We're all going to be working on the exact same document. So you remember what breakout room you are in, and you'll go down and it will say click on your group number to find your part of the table. So if you're in group, I know we don't have anybody in group 7, so I'm going to go down to group 7 for now. Go down to group 7, and there is a spot for everybody in our breakout room for us to do it individually. But what I'd like you to do, you put your name, Sarah, and then I have started possibly a model for you to begin. Now, you don't have to use this, but it's a starting place. And so when you click on it, you click on the actual picture, it comes up and it says edit. You click on the edit and it's going to take you to the drawing part of this document. And this is when you can add details to explain the phenomena that's happening in your ice and alcohol cup. So you may want to oh gosh, I want to add a line here, and I'm going to add a line. I'm going to add another line, and that is a liquid, and I'm going to add text to it, so I can add text to it, and this is going to be the alcohol, and then maybe you want to say, well, gosh, what does that alcohol look like? What's that model? What does it look like at the particle level? Maybe I want to add some shapes to it. So you can do that all on here, and you can just put and make them and add to your drawing. And then once you're done with that, you just hit save and close, and it goes back into your picture. Above it is your explanation. I want you to explain what is happening in that alcohol and ice phenomenon. Okay? What are you figuring out about it? What are you noticing? And I put this question, and different groups have different questions that might help you create your explanation. You don't have to use those questions, but it might assist you as you think through this. Okay, so the key here is when you get into the drawing, you hit edit, and then you can use those tools and hit save and close, and it'll come back. So you will have 8 minutes to work on this. And I Casey, would you mind going ahead and saying a quick overview of what you're going to do in the 8 minutes in your breakout room?
So we're using our breakout room for our alone zone time, correct?
Correct.
Okay. And so then within there, we're building a model of what we saw happen with the ice cubes and the alcohol, and we can use the questions to guide our model and our explanation.
Correct. And the reason, and if you have problems with any of the tools, and if you wanted during your alone zone time, even though I asked you to do it alone zone, sometimes you just need help because I'm not quite sure how to use this tool. You've got some other people in the room, other scientists and engineers who can assist you. Okay? All right, you'll have 8 minutes. I'm going to let you go back into your breakout rooms. Okay, scientists and engineers, I know you're still working on your models and explanations, and I know Carmen was just holding up her cup, so I know she was still looking at what is happening with that alcohol and ice. But let me share with you, I'm just going to gently continue to move us along. And so what we like to do next is we're going to do this next part as a small group in your breakout rooms. Again, this is time for you to discuss. You're going to look at other people's models and explanations. And working as a team, I want you to look at another groups and I would like for you to choose one and identify something that's similar to one of your models from your groups and a difference and make a comment about it, like how this is similar and how this is different based upon yours. And then also to ask one clarifying question about a different group member's model. Okay, you can do this as a group as you're making your comments. And the way you make comments, if you will notice, you can go when I scroll down, I can make a comment about Mackenzie's. I can say ice cubes placed in the alcohol will sink to the bottom of the container. I can add a comment right here and say, yeah, I included that in mine as well, that they were sinking, and just click on the comment. I can also add a comment to the drawing. If I click on the drawing, there is a comment placed there at the side. So there are 5 groups, and I would like to see at least 3 comments from all 5 groups. So I should see about 15 comments on the side as we look through here. Okay, you can divide and conquer if you like, of where one person looks for similarities and somebody else looks for differences, but you can discuss it and do it as a whole group as well. Okay, you are only going to have 6 minutes. I'm watching our time on this, and I know that you're in an advanced class that you can do this very well. So 6 minutes in your breakout room, you're looking for something similar to a model that you or somebody in your group made, a difference, and then ask a clarifying question. So 3 different types of comments. Thumbs up? Okay, I'm going to go ahead and move you back into your breakout rooms. Okay. Scientists and engineers. Wow, you were busy in the last 6 minutes. Really analyzing. Was there a model that you observed that said, wow, that really helps me understand what was happening in that ice and alcohol phenomenon? And whether it could have been your model, it could be somebody else's model. Was there a model that you really liked their explanation and how they put it together?
Yes, the one in group 4.
The one in group 4. Which one in group 4?
The ones that had the bubbles afterwards, so you can see the ice sinking and then going back up and releasing the little bubbles.
So let me make sure I'm sharing my screen. So this one, who was that? Martha? Martha, was it this one? I think I'm in group.
Typical, I'm talking, but I'm in mute. Sorry. Yes, that was the one with the little bubbles coming out.
Okay, so this one was
That
helping.
one. Uh-huh.
Okay. So
That kind of helped me understand it.
So how did it help you understand it, Martha?
Because I can see the chemical reaction happening. So by falling in the alcohol and then hitting the bottom and then moving back up, not all the way to the top, but like almost staying like 3/4 to the bottom and releasing the bubbles, it kind of make more sense to me because I can see what's going on in the ice actually melting, but releasing the oxygen.
Okay. Donna, you wrote this, you created this model. Would you like to kind of add some thoughts to what from Martha?
Well, I was just saying that it seemed to me that because there was a correlation between the release of the gas and the movement of the ice cubes, just like she said, moving in the cup, and that then because of the and then the bubbles just adhering to the side of the cup. I mean, it's just kind of what happened.
Okay. Did that happen in everybody's cup? Did everybody see bubbles adhere to the side? Oh, So we had some that didn't. I see Casey shaking her head, Raul shaking her head. Well, that didn't quite happen in mine. Interesting. So maybe not a consistent pattern among others. I'm wondering, does anybody else have something they would like to add about this or question this model, and that they had that maybe it didn't help them learn, but they saw another model that did help them explain it? Did everybody see bubbles? Maybe that's where we need to start. Oh yeah, everybody saw bubbles. So what was happening? What did the bubbles represent?
It could represent the gases trapped in the ice, and as the ice is melting, the gases in the ice is released, and that's why we see the bubbles.
Okay, so it's just a thing of the actual bubbles are just from the release of it melting. So is melting, remember going back to our phase changes, and we have melting, and when something melts, is that a physical change or is that a chemical change?
It's a physical change.
It's a physical change. So when we saw the bubbles and that ice was melting, is that representing a phase change of melting? A physical change or a chemical change?
Or it could be both, because we saw the ice melting and diminish in size until there's no more ice. So that is the physical change because it's a melting process. But could there also be something in the ice that reacted with the alcohol that might have released some of the gases in the form of bubbles?
And it couldn't be a chemical change because we eventually would be able to bring the melted ice, or liquid back into an ice state.
Yeah.
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 So it could be both because there's a physical change on the ice and then also a chemical change because like somebody noted on the chat that yes, release of gases or in the form of bubbling is an evidence of chemical change.
So I'm wondering, when I take a drink of water or soda and I take a straw and I blow into it, and then I have bubbles in there, is that a chemical change in my drink?
Mm-mm.
So sometimes just seeing bubbles doesn't mean that there's a chemical change. So I'm wondering, what other models were that you thought, if anybody, that this kind of helps me understand what's happening with this phenomenon? Maybe there's another model adding to Donna's model that can help us explain this phenomenon.
I think group 2, Monique's diagram did a good job of helping me visualize it.
Okay, I'm gonna move up to group 2. Let's see, Monique. Okay, Monique, you're gonna have to explain your model to everyone.
Okay, so in my model here, I identified the alcohol, and I think I should have been a little bit more descriptive, but down below on the left side, we have the ice. And then what I noticed is that as the ice got smaller or melted, it seemed to almost float on top of what I'm assuming is the melt. I'm trying to put my student hat on. And so what I'm assuming is as it's getting smaller, the melting is either going up or down. And so, but the fact that the ice was at the bottom to begin with and didn't float, it makes me believe that since it's still the same liquid, it's going to still be at the bottom. And so what that makes me think is that if it's at the bottom, then it's going to be denser, or I'm trying to think of the verbiage, the kiddos use, but anyways, yeah. So to the right, all I did was just show that the bottom portion here have more tightly packed, and that they are denser, and the alcohol is not as dense. So that's kind of what my model is showing. I didn't get a chance to do an explanation.
That's okay. What questions does anybody have from Monique and her model? I'm going to switch cameras here for a moment. Let me stop sharing. Let's see. I want us to think about, let's see. And now you really have to talk, and I can't see anything on the chat, so I'm too far away. But I want us to think about, what did you observe in your cup? What did you observe? What was happening to the ice cubes?
They were getting smaller.
They're getting smaller. What else?
They were starting to float.
Starting to float as they're getting smaller. Is that what happened?
Mm-hmm.
Yep.
Okay. So the ice cubes floated as they melted. Okay. I want us to think about this. What if that's the effect, that the ice cubes were rising, they were floating as it melts? What was causing that to happen?
I think Monique's example kind of showcases what caused that, that those ice cubes were becoming less compacted, right? They were becoming less dense, so then they could.
Okay, so
Oh.
you're so
What
they're
the temperature differences between it?
Less dense. Yes, that was my thinking.
they're becoming less dense. Why are they becoming less dense?
Size.
Because there's
Temperature
less of the
difference between-
material.
Less of the material. And why is there less of the material? What's happening to them?
They're melting.
Melting.
They're melting, right? So the
Mhm.
ice cubes, as they melted, they become less dense. Now, scientists and engineers, I'm going to when we say density, dense a lot, but what does that really mean? What does this word mean, dense?
The ratio between mass and volume.
Yeah, the number of particles in the stuff, right? The amount of stuff in there, right? So they become less dense. And I'm going to make sure we understand that word because that's a key word, right?
Mhm.
Less dense, and so they begin to float. What is causing them to melt?
The heat from
Temperature.
alcohol, because the alcohol is at room temperature, and then we took the ice from the freezer, so there's a temperature difference. So the heat from the alcohol is causing the ice to melt.
So we have some energy transfer.
Yes.
Is that what I'm trying to say? It's energy. So when we think about the word melted, what is causing it to melt? We saw that they were melting. What's causing the ice to melt?
They're gaining energy and moving, the
Mhm.
molecules are moving faster to go from a solid state to a liquid state where they slide past each other.
Okay, good. Energy transfer.
Transfer.
And the energy is coming from where? Where's the energy going from?
The alcohol to
Alcohol.
From the alcohol.
From the alcohol to the ice.
Ice.
Okay. So the ice is taking in what from the alcohol?
Energy.
What kind of energy?
Thermal.
Thermal energy, heat energy, right? And it's taking it in. And so the effect on the ice cube is that it's melting, right?
Mm-hmm.
Yeah. And as that ice cube melts, it begins to float because it's becoming less dense than what? Less dense than what?
The liquid.
Alcohol?
The water.
The alcohol.
Than the alcohol.
Less dense than
The solid ice cube.
What do you think was on the bottom?
The ice
The
cube.
melted ice.
The melted
Water.
The liquid.
Oh, the liquid. Water.
Became less dense than the melted water, right? The liquid water.
Liquid water.
Right? And if we think back to what we saw earlier, your very, very first I see, I think, I wonder, what did we notice about ice cubes in alcohol and ice cubes in water?
They melt faster. And they
In water,
sink.
they floated.
The ice floated in water.
Yes. Yes. So if we think about what is happening, what's our explanation for what's happening in this ice and alcohol phenomenon? What is happening? What's the causes of it?
Well, for one, there became a change in the composition of the liquid in the glass, because like you said, when the ice melted, so there would be more water at the bottom of the container. make the ice less dense than that part of the mixture in the cup.
So when you talk about your system
Mhm.
of what was in that system, what I'm hearing you say is that in the system we started with only two things,
Mhm.
alcohol and
And
ice.
the ice.
But what changed in that system was we ended up with some water, right?
Yes. Mhm.
Our model. Scientists and engineers, I'm going to give you a moment. I'm going to have you go back into your explanation and take a moment if you'd like to revise your explanation based upon some of this new knowledge that you have. So just give you a moment to do that while I switch cameras.
Oh, no.
How do I go back to
Okay. So I'm cognizant of our time together, and I know we're over, but I'm just going to kind of wrap this up so that we can put a bow on it. So what we figured out is that we have, and we could spend more time, we would do this, that ice is more dense than alcohol, but less dense than water. We could talk more about energy and how the energy moves from high to low, mainly if I was doing this in a high school system. And we could talk about the thermal energy being moved, being that the alcohol is an exothermic and the ice is an taking in the energy, an endothermic. And we're doing that through our cause and effect. Nobody really mentioned anything about condensation, but I had condensation on my cup. We could have gone there and talked about the system, the air system on the outside if we wanted to, and that the heat being removed from the surrounding air was causing the condensation on your cup if you had any. So this is where this lesson could have gone. But what I want us to think about is what evidence, what's putting your thinking about what was the sources of evidence did you have to support your explanation? Give you a moment just to kind of quietly think about what sources of evidence did you use to support your explanation? Would you like to share out what was some of the sources or source that you used to develop your explanation? You can put it right into the chat if you'd like. Yeah. Casey's putting it in. You know, it comes from your video, it comes from your own experiences, your visual observations. Yeah, our visual understanding, what we saw are some of our observations that we created. Putting on your teacher hat for a moment. Based upon your birthday month, whether you're January, April, May, or August, or September through December, I'm going to ask you to think about each of these individual questions. How did this approach to figure out the sense making, to figure out what was happening in this alcohol ice and phenomena, how did it lead you as a student to use cross-cutting concepts to organize your thinking? If you're January, April. If you're from May or August, how did it help you? How did this way of instruction help you construct an explanation based on evidence? And if your birthday month is from September or December, how does it help you understand the core ideas that were needed to make sense of the phenomenon. Now I'll give you a moment to think about that, and then just go ahead and record your thoughts in the chat. Perhaps if you haven't done it already, go ahead and hit. We'll do a waterfall. 5, 4, 3, 2, 1. Waterfall. And you can put those in. So as we think about, I can see great things coming through from thinking about energy, matter, cause and effect, contrasting the models, organizing their thoughts. There were some really key things in this lesson that I was trying to hit at. And when we look at our core ideas, all matter of the universe is made of particles. There's this energy transfer during an event. And our U1s, right? When we have our U1 of our standards, being able to use evidence from observations and or scientific investigations, that's part in developing a model and maybe changing it as we learn. Those were some of the key things when I look at our core ideas of what I was trying to teach in this lesson. But when I look at the other two dimensions, when I look at the science and engineering practices, I was having you ask questions, I was having you develop and use models, and I was having you construct and revise explanations. In addition, I gave you some lenses to look in, and maybe you didn't even think about using these lenses, but we just did it naturally, of what were the patterns that we were noticing, the cause and effect. Where is the energy coming from? And systems and system models. So this little piece was in all three dimensions. What questions do you have before we end our time together?
Was it really water or was it just ice on the video?
It was really water. Well, I want to thank you for your time and thank you for your willingness to stay over 10 minutes. I appreciate that. And I know that you will get these slides and the other